Welcome to this video. Today, we'll be solving LeetCode problem number 1535, find the winner of an array game. This problem challenges us to simulate a game using an array and determine the winner based on specific rules. Stick around as we dive into the solution and explore different approaches to tackle this interesting problem. In this problem, you are given an integer array called ARR, which contains distinct elements, and an integer k. The goal of the problem is to determine the winner of a game played according to specific rules. The first step in the game designates the first element of the array, ARR, 0, as the initial winner. Then, the game proceeds in rounds. During each round, the current winner competes against the next element in the array. If the current winner is greater than the next element, the current winner remains the winner and moves on to the next round. However, if the next element is greater, it becomes the new winner. The game concludes when a player achieves k consecutive wins. If no player achieves k consecutive wins after traversing the array, the winner is simply the largest element in the array. Your task is to return the winner of this game based on the rules outlined. The output of this problem is a single integer, which represents the winner of the game. Let's explore a few examples to understand the mechanics. In the first example, the input array is 2, 1, 3, 5, 4, 6, 7, and k is set to 2. The game starts with 2 as the initial winner. In the first round, 2 competes against 1 and wins, achieving 1 consecutive win. In the second round, 2 competes against 3. Since 3 is larger, it becomes the new winner, and its consecutive win count resets to 1. This process continues as the winner changes based on comparisons, and the game ends when a player achieves 2 consecutive wins or when the array traversal is complete. Continuing with the first example, after 3 becomes the new winner in round 2, it competes against 5 in round 3. Since 5 is larger, it becomes the new winner with its consecutive win count reset to 1. Next, 5 competes against 4 in round 4 and wins, achieving 1 consecutive win. In round 5, 5 competes against 6, and 6 wins, resetting the count again. Similarly, in round 6, 6 loses to 7, making 7 the new winner. As the array traversal ends, the largest element, 7, would have been the winner if no player achieved k consecutive wins. However, the game ends earlier with 5 as the winner because it achieved 2 consecutive wins during the process. In the second example, the input array is 3, 2, 1, and k is set to 10. Here, 3 starts as the initial winner. In round 1, 3 competes against 2 and wins, achieving 1 consecutive win. Then, in round 2, 3 competes against 1 and wins again, increasing its consecutive win count to 2. However, since k is 10, the game doesn't end yet. After reaching the end of the array, no player has achieved 10 consecutive wins. In this case, the winner is simply the largest element in the array, which is 3. Therefore, the winner of this game is 3. In the third example, the input array is 1, 25, 35, 42, 68, 70, and k is set to 1. As always, the game begins with the first element, 1, as the initial winner. In the first round, 1 competes against 25. Since 25 is larger, it becomes the new winner, and its consecutive win count is set to 1. Since k is 1, the game ends immediately when any player wins a single round. Thus, the winner of the game in this case is 25. This example demonstrates how the game concludes early when k is minimal. Lastly, the problem constraints remind us that the solution must handle large arrays and values of k efficiently, while edge cases like small arrays and early termination due to low k should also be considered. To solve the problem of finding the winner of the array game, we explored a few different approaches. The challenge involves simulating a game where a current winner is compared with the next element in the array repeatedly. This process continues until the winner either achieves k consecutive wins or we reach the end of the array. The array elements are distinct, and its size can go up to 100,000, which is a key constraint to keep in mind. One straightforward way to solve this is the brute force approach. Here, we simulate the game exactly as described. For each round, we compare the current winner with the next element. If the current winner wins, we increment their win streak. Otherwise, we update the winner to the next element and reset the streak. We repeat this process until someone wins k consecutive rounds or we traverse the entire array. However, this approach can be inefficient. In the worst case, with n being the length of the array, the time complexity is n*k. This happens when we repeatedly loop over the array, making it unsuitable for large inputs or very high values of k. Let's look at a more efficient way to solve this problem. Instead of simulating the entire game step by step, we can optimize the process by utilizing the constraints and properties of the array. Since the array contains distinct elements, the largest number in the array will always win against every other number. This insight allows us to simplify the problem significantly. The game effectively ends as soon as the largest number achieves k consecutive wins or when it becomes the winner by default after all comparisons are made. To implement this, we keep track of the current winner and their win streak using a sliding window approach. We stop the simulation as soon as the winner achieves k consecutive wins. Additionally, if the value of k is larger than n, the largest number in the array becomes the winner because it will eventually defeat every other element. This optimized approach has a time complexity of n, as we only need to iterate through the array once. It is efficient, scales well for large inputs, and avoids the unnecessary repetition of the brute force method. The chosen strategy builds on key observations about the problem. The most important insight is that the largest number in the array will ultimately win all comparisons. Therefore, the challenge reduces to determining how quickly this number can achieve k consecutive wins. If k is greater than or equal to n, there's no need for further computation because the largest number is guaranteed to be the winner. By simulating the game only once and efficiently tracking the current winner and their win streak, we can avoid redundant computations and achieve the desired result. This approach was selected because it is both simple and efficient. It eliminates unnecessary iterations by stopping as soon as a winner is found. Furthermore, it leverages the fact that the array elements are distinct, which lets us make decisions confidently without additional checks. With a time complexity of n, this method is well suited for handling the problem's constraints, including large input sizes. When comparing the approaches, there are clear trade-offs. While the brute force method is conceptually simple, it is computationally expensive, especially when the value of k is high. On the other hand, the optimized approach significantly reduces runtime by leveraging early termination and the distinct nature of the array. This makes it far more efficient without sacrificing clarity. Alternative methods, such as pre-computing the largest element in the array, do not improve the time complexity beyond n, and they can add unnecessary complexity to the solution. Ultimately, the optimized approach strikes the right balance between efficiency, simplicity, and scalability. It is the best choice for solving this problem within the given constraints, ensuring both clarity and optimal performance. To solve the problem of finding the winner in this array game, we simulate the rounds step by step. First, we initialize two key variables. The current _winner starts as the first element in the array, since no comparisons have been made yet. We also set consecutive _wins to 0, which will help us track how many rounds the current _winner has won in a row. Next, we iterate through the array starting from the second element. For each element, we compare it with the current _winner. If the current _winner is larger, it wins this round, and we increment consecutive _wins by 1. However, if the current _winner is smaller than or equal to the current array element, the new element becomes the current _winner, and we reset consecutive _wins to 1, as this is the first win for the new winner. This iterative process allows us to simulate the rounds of the game efficiently. Now, to optimize the process, we introduce an early termination condition. After each round, we check if the consecutive _wins for the current _winner has reached the value of k. If it has, we can immediately return the current _winner as the final result, since the rules of the game guarantee that this number is the winner. Additionally, we handle the edge case where the loop completes without any number winning k consecutive rounds. In such a scenario, the largest number in the array will always be the winner. This is because the largest number will continue winning every comparison once it becomes the current _winner. Therefore, if no number meets the k condition, we simply return the maximum element from the array. Understanding why the largest element always wins is key to this problem. During the iteration, if no number manages to win k consecutive rounds, the loop ensures that the largest number eventually becomes the current underscore winner. Since there are no elements larger than the largest number, it will win every subsequent comparison. This insight guarantees that the algorithm is robust. Another important optimization is the early termination condition, which allows us to exit the loop as soon as a number wins k consecutive rounds. This significantly reduces unnecessary computations, especially when k is small. Furthermore, the algorithm naturally handles edge cases like when k is greater than or equal to the array length. In such cases, the largest number will always win by default. Finally, even if the array contains duplicate values, the algorithm treats each occurrence independently, ensuring correct comparisons throughout. To implement this efficiently, we utilize a few simple data structures. The current underscore winner variable keeps track of the number currently in the lead, while consecutive underscore wins counts how many rounds this number has won in a row. These two variables are updated dynamically as we iterate over the input array. The array itself is processed in a single pass, with each element compared exactly once. This gives our algorithm a time complexity of O(n), as the number of comparisons scales linearly with the array size. Additionally, the space complexity is O(1), as we only use a constant amount of extra memory for the current underscore winner and consecutive underscore wins variables. This makes the solution highly efficient and well suited for large inputs. Let's walk through an example to see how the algorithm works in practice. Suppose the input array is 2, 1, 3, 5, 4, 6, 7, and k is 2. We start by initializing the current underscore winner to 2 and consecutive underscore wins to 0. First, we compare 2 with 1. Since 2 is larger, it wins this round, and consecutive underscore wins becomes 1. Next, we compare 2 with 3. This time, 3 is larger, so it becomes the new current underscore winner, and we reset consecutive underscore wins to 1. We continue this process, 3 loses to 5, so 5 becomes the current underscore winner, and consecutive underscore wins resets to 1 again. Then, 5 beats 4, increasing consecutive underscore wins to 2. At this point, the condition for early termination is met, as 5 has won 2 consecutive rounds. The algorithm stops and returns 5 as the winner. Finally, let's discuss some edge cases. If the array is very small, such as 1, with k equals 1, the only element in the array is the winner. The output in this case would be 1. For cases where k is much larger than the array length, like 3, 2, 1, with k equals 10, the largest number, which is 3, will ultimately win, as it will remain the current underscore winner once it's reached. Another interesting scenario is when all elements are equal, such as 4, 4, 4, with k equals 2. Here, the first element wins since every comparison results in a tie, and consecutive underscore wins increments without resetting. The output would be 4. These examples highlight how the algorithm effectively handles a wide range of input configurations while maintaining its efficiency. This solution efficiently simulates the game described in LeetCode problem number 1535. Here's a detailed explanation of how the code works. 1. Initialization. We start by assuming the first element of the array, arr, 0, is the current winner. Additionally, we initialize a consecutive underscore wins counter to 0. This counter tracks how many rounds the current winner has consecutively won. 2. Simulating the game. We iterate over the array from the second element onward, index 1 to the end, and compare each element with the current winner. If the current winner is greater than the next element, it wins the round, and the consecutive underscore wins counter is incremented by 1. Otherwise, the next element becomes the new current winner, and the consecutive underscore wins counter is reset to 1 because the new winner has just won its first round. 3. Checking the win condition. During each iteration, we check if the consecutive underscore wins counter has reached k. If it has, we immediately return the current winner as the result. This ensures that the solution is efficient and stops early when a winner is determined. For returning the maximum element, if the loop completes without any element achieving k consecutive wins, the maximum element in the array will inevitably be the winner. This is because the largest number cannot lose to any other number, and the traversal ensures that it will eventually become the current underscore winner. This approach is efficient with a time complexity of O(n), where n is the length of the array. This is because we perform a single traversal of the array and compare each element at most once. The space complexity is O(1), as we only use a few variables to keep track of the current state of the game. This makes the solution optimal for the given problem constraints. Here, we begin by importing the necessary Java utilities and defining the solution class. Within this class, the getWinner method is implemented to solve the problem. The method takes two inputs, an integer array arr, which represents the sequence of numbers, and an integer k, which specifies the number of consecutive wins needed to determine the winner. We initialize two variables. Current winner is set to the first element of the array, assuming it as the starting winner, and consecutive wins is initialized to 0 to keep track of how many consecutive wins the current winner has achieved. Next, we use a for loop to iterate through the array starting from the second element. During each iteration, we compare the current winner with the next element in the array. If the current winner is greater, it wins the round, and we increment the consecutive wins counter. Otherwise, the current winner is replaced with the next element, and the counter resets to 1. If at any point the consecutive wins counter reaches the value of k, the current winner is immediately returned as the result. After completing the traversal of the array, if no element has achieved k consecutive wins, the function simply returns the current winner. This will be the maximum element encountered during the traversal, as the current winner is updated anytime a higher value is found. The method ensures the game simulation is efficient, and by the end of the loop, we either identify the winner through consecutive wins or default to the highest value in the array. Finally, the method concludes, and the class is ready for use. Here, we start with example 1, where the array is 2, 1, 3, 5, 4, 6, 7, and k is 2. First, we initialize current_winner to the first element, which is 2, and set consecutive_wins to 0. In round 1, we compare the current_winner, 2, with the next element, 1. Since 2 is greater than 1, 2 remains the current_winner, and we increment consecutive_wins to 1. In round 2, we compare the current_winner, 2, with the next element, 3. This time, 2 is less than 3, so the current_winner is updated to 3, and consecutive_wins is reset to 1. Moving to round 3, we compare the new current_winner, 3, with the next element, 5. Again, 3 is less than 5, so 5 becomes the new current_winner and consecutive_wins is reset to 1. Finally, in round 4, we compare the current_winner, 5, with the next element, 4. Since 5 is greater than 4, 5 remains the current_winner, and we increment consecutive_wins to 2. Now, in the same example, we see that consecutive_wins has reached k, which is 2. As a result, the function returns 5 as the output. Moving to example 2, the array is 3, 2, 1, and k is 10. We start by initializing current_winner to 3 and setting consecutive_wins to 0. In round 1, we compare the current_winner, 3, with the next element, 2. Since 3 is greater than 2, 3 remains the current_winner, and consecutive_wins increments to 1. In round 2, we compare the current_winner, 3, with the next element, 1. Again, 3 is greater than 1, so it remains the current_winner, and consecutive_wins increments to 2. At this point, the array is fully traversed, but consecutive_wins has not reached the value of k, which is 10. Therefore, the function returns the maximum element in the array, which is 3. Finally, in example 3, the array is 1, 25, 35, 42, 68, 70, and k is 1. We begin by initializing current_winner to the first element, 1, and setting consecutive_wins to 0. In round 1, we compare the current_winner, 1, with the next element, 25. Since 1 is less than 25, the current_winner is updated to 25, and consecutive_wins is reset to 1. This time, consecutive_wins equals k, which is 1, so the function immediately returns 25 as the output. To analyze the time complexity of this solution, we start by breaking down its operations. First, the initialization of current_winner and consecutive_wins is a simple O(1) operation, as it involves setting up two variables. Then, we move to the main part of the algorithm, where a for loop traverses the array starting from the second element, at index 1. In the worst-case scenario, this loop will iterate n times, where n is the size of the array. As a result, the traversal contributes n to the time complexity. Inside the loop, for each element, we perform a constant number of operations, a comparison to check if the current element is smaller or larger than current_winner, followed by assignment operations and a check for whether the consecutive win condition is met. Each of these operations takes O(1) time per iteration, and since the loop runs O(n) times, these steps together contribute O(n) as well. This means that the operations inside the loop are linear in nature. After the traversal, there's a final fallback mechanism where the algorithm simply returns current_winner as the result if no element achieves k consecutive wins. This is a single O(1) operation. Combining all these steps, the overall time complexity of the solution is O(n) in the worst case, where n is the length of the input array. Moving on to space complexity, it's determined by the additional memory used apart from the input array. We only use two variables, current_winner to store the current leader and consecutive_wins to count the current streak of consecutive wins. Both of these require O(1) space. Since the input array is directly used and no additional data structures are created, the total space complexity remains O(1). This makes the solution highly efficient in terms of memory usage. The time complexity can also be analyzed through best, average, and worst-case scenarios. In the best case, the first element of the array achieves k consecutive wins very early, such as within the first k comparisons. Here, the loop terminates early, and the time complexity becomes O(k). When k is much smaller than n, this is significantly faster than the O(n) worst-case scenario. In the average case, the loop will traverse a portion of the array before determining the winner, leading to a time complexity still bounded by O(n). Finally, in the worst case, the loop iterates through the entire array because no element achieves k consecutive wins, and the maximum element in the array becomes the winner. This scenario results in O(n) time complexity. These cases highlight how the algorithm adapts to different input conditions, optimizing its runtime whenever possible. When comparing this optimized approach to a brute force method, the advantages become clear. A naive solution might simulate all possible pairwise comparisons repeatedly for each round of the game, leading to a worst-case time complexity of O(n squared). This inefficiency arises from redundant comparisons and lack of early termination. In contrast, the current optimized solution avoids this by maintaining a single current_winner and a count of consecutive wins, reducing unnecessary operations. As a result, the time complexity is brought down to O(n). To mathematically confirm this, we note that the algorithm traverses the array once, performing O(1) operations per element. There are no nested loops or recursive calls that would multiply the complexity. Additionally, space usage remains constant since no extra data structures are used. This proves that the time complexity is O(n), and the space complexity is O(1), making the solution both time and space efficient. When working on this problem, there are some common mistakes to watch out for. First, misunderstanding the game logic can lead to incorrect solutions. Remember, the current winner only changes when the next element in the array defeats the current winner. This means your simulation needs to capture that specific rule accurately. Another common pitfall is stopping the simulation too early. Some might assume the game ends as soon as one element defeats k consecutive opponents. However, the game only concludes after processing the entire array, so make sure your solution accounts for all elements. Additionally, brute force approaches, where you repeatedly iterate through the array for comparisons, can quickly become inefficient with a time complexity of O(n squared). Instead, aim for a more optimized approach. Lastly, edge cases like k being larger than the size of the array, arrays with all identical elements, or arrays with just one element are often overlooked, so ensure you handle these scenarios carefully to avoid runtime errors or unexpected behavior. Overcomplicating the solution is another mistake to avoid. For instance, using data structures like heaps or trees unnecessarily can increase the complexity of your code. Instead, focus on simpler methods like simulating the game with a sliding window approach, which can achieve an efficient O(n) time complexity. From an interview perspective, the key to solving this problem efficiently lies in recognizing the iterative nature of determining the current winner. Once an element defeats k consecutive opponents, you can return it immediately, which saves unnecessary processing. Interviewers may also evaluate how clean and optimized your code is, so prioritize clarity and avoid over-engineering. Be prepared for follow-up questions like how you'd handle extremely large arrays or optimize memory usage, as these are opportunities to discuss trade-offs between time and space complexity. Lastly, ensure you emphasize edge case handling in your explanation, such as how your solution deals with arrays where all elements are equal or when k exceeds the array length. This problem can also be connected to several related challenges on LeetCode that involve similar concepts. For example, LeetCode 121, Best Time to Buy and Sell Stock, focuses on identifying optimal subsequences, while LeetCode 169, Majority Element, involves determining the dominant element in an array. LeetCode 1985, Find the kth largest integer in the array, is another problem centered around comparisons in order, and LeetCode 11, Container with Most Water, emphasizes maximizing results using array-based logic. When considering alternative approaches, a sliding window simulation is often the most efficient. This involves iterating through the array once, keeping track of the current winner and counting consecutive wins, which achieves an O(n) time complexity with O(1) space usage. However, while simple and efficient, this approach requires careful attention to edge cases. On the other hand, a brute force method might involve comparing each element with all subsequent elements to find a winner, but its O(n)² time complexity makes it impractical for large inputs. Another potential approach involves using a heap-based method, where a max heap tracks the strongest elements. However, this adds unnecessary complexity to the problem, with a time complexity of O(n) log n due to heap operations. For this particular challenge, such an approach is generally overkill and should be avoided unless specifically requested. The key takeaways here are to simulate the game logic correctly and aim for an O(n) solution by iterating through the array just once. Make sure to properly handle edge cases like arrays with all identical elements, arrays of size 1, or when k exceeds the array length. Finally, simplicity is crucial. Avoid overcomplicating your solution with unnecessary data structures or convoluted logic. By focusing on these principles, you can solve this problem efficiently and effectively while demonstrating clear, robust coding practices in an interview setting. Great work! We've solved LeetCode problem number 1535 using an effective approach. Remember the importance of understanding the problem constraints and optimizing for performance. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!